Okay. All right. So, no, I haven't graded the exam yet. Because I was thinking of being gentle with my grading scheme, but now I think I'm just going to be pretty ruthless and just, if it's wrong, it's wrong.
Give me further reasons to drop out.
Wait, you mean the picture that was already there on the page? I'll ponder that one. So, okay. Everybody was counted present for the exam in terms of your attendance. Grading, though, other than the exam, we're caught up, okay? My goal is to grade the exam on Monday, but I'll say this. I have to work this out with your materials professor, but in terms of time sensitivity, I'm actually more interested in doing some analysis on your absorption data from labs 4 and 5. So I'm probably going to do that first. So if this gets pushed back to like Wednesday or whatnot, that's why. Because I really want to get your labs done by Monday, because I want to do some of the background math to designing your concrete lab and whatnot. We're going to get back into the swing of things on homework. So you've got a homework assigned today, due on Friday. Today we are going to begin one of the most seminal topics in structural analysis, which is the construction of shear and moment diagrams. We're not actually going to do any shear and moment diagrams today, though, because all we're going to focus on today is just computing shears and moments at a particular location. Because a shear and moment diagram is just a plot of those internal responses at every location. So I want to do one location first, and then we'll look at everywhere. Okay. Did everybody get the QR code? Okay. All right. So, okay. So let's talk about shear and moment diagrams. And like I said, that there are some just sort of fundamental tasks that as engineers are sort of rites of passage that you are able to do. Okay. For example, in the land of civil engineering, the performance of the sieve analysis, like everybody just sort of knows if you can do a sieve analysis, it's one of those things like, okay, that's part of civil engineering. The construction of a shear and moment diagram is another one of those sets of tasks. Shear and moment diagrams are some of the most fundamentally useful tools for civil engineering, particularly, of course, in the land of structures. What they are is a graphical representation of the internal response of an element under flexure. Okay. For example, I have here a beam shown above, which has some pretty, I don't want to say tricky loads, but this is the type of problem that would, in my opinion, be above and beyond what I would expect you to be able to do just from Engineering 213. We did this problem, we did problems like this in Engineering 213, but to be candid, in 213 we do shear and moment diagrams, but we do them at a pretty high level. We don't spend a lot of time on them because we don't have a lot of time on them. We have to discuss forces, we have to discuss moments, we have to discuss centroids, and so by the time we get to trusses and shear and moment diagrams, we sort of only lightly touch them. You may have discussed them in a little bit more detail in Engineering 216, but in here, we're really going to focus on them. Why do we focus on them as structural engineers? Because they're critical for design. Okay? So for this beam, I propose to you that this is what the shear diagram looks like, this is what the moment diagram looks like. I say that they are critical for design because they tell us pictorially what we need to do for the purposes of sizing this element. So let's just assume for the sake of discussion that this is a reinforced concrete element in the land of something that Dr. Zatara would teach for CE 413. Okay? So what can I tell you about this beam if it was a reinforced concrete beam? Okay, so concrete is a beam, or concrete is a material that behaves very well in compression but very poorly in tension. So you place the rebar wherever there is tension. Okay? So I propose between the two supports, so we'll call this point A and point D, maybe a little bit over here to point F, I need to place my rebar or my longitudinal rebar, the rebar that goes along the length of the beam, I need to place it in the bottom of the beam right here. I need to place it in the top of the beam here. So if this beam was, let's say, rectangular, so this is what the beam looks like. From A to F, I need to place my rebars on the bottom because those are the regions that experience tension. But whereas over here, I would need to place the rebar on the top. Okay, and so there's probably going to be a little bit of overlapped rebar in this region where the stresses reverse a little bit, and also we'll need to account for development length. The other thing that we will include when we tie together our rebar in a reinforced concrete beam is what's called a stirrup. Okay, so a stirrup sort of goes around the rebar kind of like this. Okay, and so if you look along the beam like this, okay, like here's our support. The stirrups sort of go like this, okay? I propose in this region, we're going to have some tightly spaced stirrups, but out in here, the stirrups are going to be spaced more further apart. Why? Because the shear diagram tells me that wherever we have high shears, we need a higher concentration of stirrups, right? So I'm looking at this shear diagram without doing any of the math, and I can tell you, like with some specificity, what the reinforcement pattern is going to look like based on what the shear diagram looks like and what the moment diagram looks like, okay? And that's why they're so incredibly valuable. Like if we were talking about steel design, and to keep it very, very basic, the shear diagram would tell me what I need to do with my web. The moment diagram would tell me what I need to do with the flanges. If I wanted to transition the size of the element, I could use smaller flanges out here, bigger flanges over here. Okay, and I can get a lot of that by just looking at it. Okay. Now, one of the things that I'm going to focus on over the next few lectures, over the next probably like 2.5 weeks, is not only do I want you to be able to construct shear diagrams, but I want you to be able to look at shear and moment diagrams, but I want you to be able to look at them and tell me whether or not they make sense or if they're accurate. I mean, I meant what I said on day one, that like I'm not blind to the introduction of AI in modern landscape. It's there, it's not going anywhere, okay? But if you remember, I showed you 3 moment diagrams in lecture 1, and I said which one was right, and they were all wrong, right? So, for example, I can tell you that these are probably right based on their shape. For example, if I look between, we'll call it A and C, okay? Between A and B, right here, there is no load. Between between B and C, there is no load. The beam has nothing on it. So I know that the shear diagram should be constant like a stair step. I know that the moment diagram should be linear, okay? I know that between here and here, we have a distributed load. So my shear diagram is linear, my moment diagram is parabolic. I know that's right, okay? I have a concentrated load of 60 kips right here. So that causes a jump in the shear diagram, a change in slope in the moment diagram, okay? I know I got a concentrated 180 foot kips right here. What does it do to the shear diagram? Not a thing. What does it do to the moment diagram? Sudden jump right there, okay? Those are patterns that I can recognize because I know how shear diagrams work and how moment diagrams work. I want you to get to that same place, okay? So that you can look at this moment diagram and go, does that look right or does that look wrong, okay? And those are the types of things I kind of want to focus on throughout the next few lectures, okay? Does that make sense? Okay, now in order to get there, we need to sort of start from square one, okay? And so what we need to do is we need to start with what shear diagrams and moment diagrams are and how do we get there, okay? Now a shear diagram and a moment diagram is a graphical representation of the internal response across a beam or across a frame. So I want to start by figuring out what is the internal response at a single point, okay? So the idea is we'll first figure out how to get the response at a single point, then we will get the response at every point, okay? So we're going to start by looking at internal shears and moments and beams, and for the vast majority of our coverage of shear and moment diagrams, we're going to focus on beams. We're going to have one lecture where we're devoted to frames, and really the only difference is a shear and moment diagram for a frame is just one for a beam face up like that. It's really no different, okay? Now, like I said, we're going to determine shears and moments at a given point, and so I now want to go back to this, okay? I showed you this a little bit earlier in the semester, and I said, okay, if you take the samurai sword or a lightsaber through a beam and you split that into two components, internally you could get three unknown responses: an axial force, a shear, and a moment, okay? When we were looking at trusses, we were looking at the axial forces. That's all we cared about, because remember, with trusses, the assumptions that we made, there was no shear, there was no moment. The truss members carried only axial force. And we also kind of looked at this from a hinge perspective. If we cut a section at a hinge, there is no moment. Now, we got to sort of consider this more generally. Now, one of the things you're probably starting to notice in this class is this class is not really a memorization class. There's not really anything to memorize, okay? This is something I would memorize, okay? What I mean by that is, so if I cut a section and I look to the left, okay, I have to make a decision as to what I'm going to consider a positive shear and a positive moment. And the same thing if I look to the right. And so the sign convention that we are going to use is that if you cut a section and look to the left, downward shears are positive. If you cut a section and look to the right, upward shears are positive. Moments. Cut a section, look to the left, counterclockwise moments positive. Cut a section, look to the right, clockwise moments are positive. Okay? Now, from a formula computational perspective, the assumption, the sign direction, or the sign convention doesn't matter, okay? Because you can always assume something, and if you get a negative answer, it just means your assumption's incorrect, okay? But for this part of the course, and for the construction of shear and moment diagrams, I argue that adhering to this sign convention means so much more, okay? And so we basically just need to say, this is positive, so that if we get the opposite answer, it's negative. Why am I being so steadfast with this? Because this sign convention adheres to the graphical technique that we're going to develop later when we construct shear and moment diagrams by hand using this graphical approach. So the idea is that we're going to be able to look at the beam and construct the shear diagram, and then integrate the shear diagram to construct the moment diagram. And we're going to do this in a very graphically friendly approach. But in order for that to work, we've got to stick to this. Okay? So this is our sign convention. This is like one of the few things that I would say, just memorize it, we're going to use it. Okay? Everybody with me on that? Okay. So I want to illustrate this by looking at a given example. Okay? So I want to compute the internal response for this beam at a particular point. Okay? Now, first off, before we start going down the rabbit hole, does everybody recognize this beam? I'm hoping you do. We've already computed reactions for this beam. We did this a few weeks ago. This was the very first problem that we did in this class when we computed support reactions. I really like in my classes to sort of like go back to things we had done before, because like you don't need to like take it on faith that these answers are right. So we computed them together. Okay, so we computed these support reactions, and I want to determine the internal response at a point 12 feet to the right of support A. Okay, so what I'm going to do is I'm going to cut a section right here, so we'll call it section 1-1. And we're going to determine what is the internal shear, what is the internal moment at that point, okay? Now, it doesn't really matter whether we look to the left or look to the right, okay? But, like I've said, I'm kind of lazy, okay? I think that there's an easier direction to look, and which direction is that, left or right? Left. Left. There's one force, one reaction here, two forces, one reaction. Let's just look this way, okay? So we're going to cut a section, look to the left. Okay, so let's see what we've got. Okay, before I go down the rabbit hole on this, let me make sure I add, oh wait, that's the wrong color. I need, do that. We know that this dimension right here is 12 feet. So it's 12 feet to the right of support A. Okay? All right, so we have our beam, okay? And we know we've got our, that's our section cut. That's where we sliced the beam out, all right? And again, this is the same idea. If I am sitting here on this table, okay, and I didn't wear the hat, so Mr. Cartwright's like, okay, I don't like that. We're cutting the table in half, right? I'm going to fall down because the table right here has some internal forces inside it keeping me upright. So that's what we're trying to figure out, is what was going on inside the beam right there. All right. Now what we'll do is we'll start off by placing our known quantities. Okay, so we know that right here we have a 35.8 kip right there. And we know we have a 20 kip right here. Okay? So 35.8 and 20. Okay? We know that from the left to where the section cut is, we know that that is 12 feet. Okay? I can do better than that. Okay, so, by the way, we know that this dimension is 6 feet. So that makes this dimension 6 feet too. And I have something I'm going to say about this dimension here, this determining these dimensions for the section cuts. I'll say that, I've been teaching this class for a long time, and actually determining these dimensions for a section cut is the one thing I think I find students making big mistakes about. For this problem, it's really easy, but for distributed load problems and whatnot, it's a little bit more challenging. And so I have a specific example I'll show you about here in a bit. Okay. Now, when we cut the section, there's an unknown shear and an unknown moment. Let's see if everybody was paying attention. Unknown shears. If I cut a section and look to the left, an unknown positive shear is facing up or down? Down. Okay. So I'm going to place a downward value right here. We'll call that V. We've got an unknown moment, which we'll call like that. One thing I'll say just right off the bat right now, so this is one area where I tend to deviate from the notation in the textbook. The textbook uses the letter S for shear. I do not, because my S's and my 5's look the same. But a lot of structural engineers will use the letter V for shear because it's a change in vertical forces. So that's why we use V. Okay. Okay. So let's see if we can determine these unknown components. And so for the shears, we'll just sum forces in the y direction. Okay. So let's sum forces in the y direction. So this is, to be clear, this is like no different than really any other mechanics-based problem that we've been doing so far. So I've got 35.8 going up, I've got 20 going down, and I've got V going down. Okay? So, bless you. Okay. So, what is V in this case? What's going on? What did I do?
No.
Oh, okay. All right, what is V?
15.
Okay, 15.8, but more importantly, positive 15.8 kips. Now, one of the things you'll notice that I'm not really indicating right here is that before what I would do is I would say, well, that's 15.8 kips, so it's 15.8 kips going down. I really don't think I need to do that here because I'm doing an internal response computation. I've already decided the sign convention off the bat, so I'm already accepting that sign convention. So because of that, I just really care if it's positive or negative. So that's a little bit of a deviation from what I've done in the past, but there's a reason for it because, before, when we were computing support reactions are more dependent upon you assuming a direction of the arrow and then telling me whether it's positive or negative. Your assumptions can change. We're already agreeing on the assumptions with this, so we don't need to do that. So that's going to be my answer, positive 15.8. So there's that. Now, summing moments, what I'm going to do, whenever we cut a section, we typically sum moments at the cut. Okay? And one thing that I'll say before we start jumping down this computation is that right now what we're doing is we're just determining values. Okay? What is the value of the shear at x equals 12? What is the value of the moment at x equals 12? When I say x equals 12, I'm saying let's assume there's a coordinate system and x equals 0 is over here, so this is x equals 1, 2, 3, 4, 5, all the way over here. That's what I mean when I say values. Okay? Later on, we're going to determine the shear at x, the moment at x. So instead of getting a value for shear, we're going to get a function for shear. We're going to get an equation. You know, some equation in terms of x, some equation in terms of x. And there's going to be a relationship between those equations. We're going to talk about that today. But we'll use it a little bit later. Okay. So let's sum moments at the cut. So this one I want you to help me with. We're going to sum moments here. Does this generate moment? Times the moment arm up? 12. Left or right? Well, left or counterclockwise or clockwise, I guess I should say. At the section cut, it's clockwise, right? So it belongs on this side. We're going to have 20 kips times the moment arm up, and that's going to be on the left side or the right side. There we go. 20 kips times 6. Does the shear generate moment? At the cut, what would the moment arm be? Keep in mind, I'm sort of drawing it over here, but really it's going through this point, right? So it would be this times the moment arm of 0. So it's not generating any moment. But this is, right? That is, so what I'm saying is these two are not equal to one another, right? So the beam's got to support the difference, okay? And I'm going to put that difference over here because I've already accepted that as my sign convention. So 35.8 times 12, that's 429.6. So therefore, 429.6 minus 120, that's 309.6. And that's it. That's it. And so before we start going any further, I'll just say your homework problem is just going to do 2 problems like that. That's it. That's all I want to focus on right now. Okay. Does this make sense? I'm hoping this is easy. Like I said, we're starting easy. We'll ramp it up as we go. Okay, now, I have here a little box here. So after we finish this example, a question, and I'm just going to read it out. Would our answer change if we changed our point of interest from 12 feet? So what I'm saying is this is the internal shear and the internal moment right there, right at that point. Okay? What if I moved that point? What if I took that point and moved it here? Would I get different answers? I think if I cut a section, let's go back to our original beam, okay? If I cut a section, let's say here, let's call it 4 foot to the right of A. If I cut a section of 4 foot and looked over here, would I get a shear of 15.8 and a moment of 309.6? No, I'd get a different answer, right? So imagine, let's think about this. Could I cut a bunch of different sections? Let's say cut a section every foot, calculate a value. Cut a section at 1 foot, 2 foot, 3 foot, 4 foot. And at each cut, write an answer, write an answer, write an answer, write an answer. Take that data, pop it into Excel, plot it. Could I do that? That's a shear diagram, that's a moment diagram. That's what they are. It's just, that's what it is. Now, that would be a pain, wouldn't it? So the idea is, can we do that a little bit more easily? That's sort of going to be our goal for the next few lectures, is to do that process, to basically plot the shear and moment at infinite points. But the way that we do that is we do it graphically. Bless you. All right, everybody good with this? Okay. Okay. Now, I want to talk about, is this not waking up? Okay. I want to talk about distributed loads, and I want to recall what we used to do. So I didn't have a problem with distributed loads, but I really kind of want to walk you through this, because I think that this animation will clarify something for you a lot better than just doing a raw example, because I think you'll see my point. Okay, so let's go back to what we did when we computed reactions. Okay, so this is really important. I focus on this. Okay, so if we have a distributed load, what we would do is to compute reactions, we said, okay, I'm going to turn it into a point load. And what I'll do is I'll put that point load right in between, and then the magnitude of that point load is the area of that rectangle, right? And then the same thing over here, the area of the triangle, put the load a third away over from the tall end. Okay, is everybody okay with that? Now watch this up here. Okay, so let's take a look at this beam. Okay, let's just digest what we have here on the screen. So I have a simply supported beam. I got a 40 kip load over here, and I have a distributed load. Now, think about if you were computing reactions for this problem. What would you do? You would say this is 2 kips per foot over a distance of 10 feet. So you would idealize that as a single point load of 20 kips, and you'd stick it 5 feet from the right of A, because this is 10 foot over. You some moments, get that as 35, that is 25. With me so far? Okay. Now, let's say that Dr. Michelson says, okay, I want you to tell me what the internal response is right here, okay? And I tell you that the internal response, I want to find the internal response at a point 6.5 feet to the right of A. So you say, well, I've got a secret weapon of structural engineering. I've got a samurai sword or a lightsaber. I'm going to cut a section, and I'm going to look to the left. I do that. This is what the beam looks like. What is this load? When I idealize this as a point load, what is it?
What is it, 13 kips?
It's 13 kips. It's not 20 kips, okay? I cannot tell you how many students in this room that I am saying this to you with right here, I'm saying it, are going to put 20 kips right here. I'm using my words. I'm saying, here it is. And they're going to put 20, okay? I said this a while back, that this right here is an idealization that we made in order to compute these reactions. But when you cut a section and look over here, this is a different free body diagram, okay? This is not 20 kips. This is 2 kips per foot over a distance of 6.5 feet. So it's 3.25 kips. In fact, every time that you cut a section through here, it's a different force and it's a different moment arm, okay? I'm telling you, there's going to be people in here that make that mistake, and so I'm really trying to prevent that from happening, okay? The idea is, and I really want you to get this in your head, is that, like, you do this idealization for the analysis at hand. Once you're done with that analysis, that idealization doesn't matter anymore, okay? Really, really, really important, okay? Everybody okay with that? Okay. Okay, now, I don't know why my pen's not liking me right now. Okay, now, like I said, we could plot shears or shear and moment diagrams the hard way by just cutting a bunch of sections, putting it in a table, and plotting it, you know, in Excel or on graph paper or something. But our goal is to be able to do this a little bit more elegantly, and I want to know them everywhere. In other words, like the problem that we just did is great for spot checking. If I want an internal shear here or an internal moment here. But if I want shear and moment everywhere, I need something a little bit more basic. Okay? So I want to graph the shear and moment along the beam. Okay. Now, I want to explain how this works by considering this beam. Okay? Now, what I'm saying is I've got some beam subjected to some arbitrary load. Okay? So I'm just calling it W of X. Just some function of some load. I've got it pointing upwards because it makes the math a little bit easier in the derivation, but I mean, I know that normally you probably have load going downward, but that's just for the purposes of the math. Speaking of the math, notice how I've got a nice little coordinate system here on my beam. I've got an x-axis and a y-axis, and I'll say my origin is over here on this side of the beam. All right, sound good? Okay. Okay, my pen does not like me right now. Okay. Now, let's go back to Math 229 land. Ooh, I'm breaking out some calculus. I'm sorry, we're doing calculus today. Do you remember from calculus, and whether it was discussed in calculus or physics, I really don't know, but I'm sure somebody mentioned the physical meaning of this term dx, okay? So if you have a graph of a function, f of x, and you talk about an element or a slice of that function, and you say it's dxy, essentially what you're saying is that it's infinitesimally wide. It's a really, really, really tiny slice of that element, right? Okay, so the term dx, what I want you to think of in your head is that dx is just a really, really, really tiny width, okay? So I'm going to slice out a little bit of an element that's dx wide. So some distance x from the origin will slice out an element, and then I'm going to zoom into that element over here. Okay? So what I've done is I've said, okay, let's take this element, put it under the microscope, and this is what we have here. Okay? So what do I have under the microscope? Okay? So let's see if I can sort of digest what we have here. Okay? First off, so I have the width of the element here is dx, the width of the element is dx. This is just me blowing it up a little bit. So a couple things. Over here, the load is variable. It's changing. It's a function. But over here, I have like a constant load. Why did I do that? Okay. Well, I'm saying the reason I did that is because, yeah, the load is variable, but I'm investigating that over a really, 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 really tiny function. Okay? I mean, this is not that crazy. I mean, when you first start to learn about integrals, right? And you say, I mean, what is an integral? An integral is used to define the area under the curve. So how did you define an integral? You said, okay, I've got a curve. I'm going to take the area of that little rectangle, and then I'm going to make those rectangles really, really tiny and sum them up, right? A Riemann sum. It's kind of the same idea. Okay? So I'm going to say over this little rectangle, we'll say the load is constant. Okay? Now, that's the first thing to explain. What about this? What's going on here, on the ends? So I propose I have a shear on this end, and I have a shear on that end. They're drawn according to their positive sign convention, because this would be sort of on the right side of the section cut. So if I cut a section, look to the right, cut a section, look to the left. I know that seems a little backwards, but again, I'm cutting and looking that way. So I've got a shear here and a shear here, but what's up with this? I've got a shear up and a shear down, but instead of being V and V, I'm saying this is V plus some increment. Same thing with the moment. I've got a moment, but I've got a moment plus some increment. Okay? What I am proposing is that from point A to point B, the shear changes. The moment changes. Okay? What I'm trying to do is quantify that change. If I can do that, if I can figure out how much the shear and moment changes from point to point to point to point, that's my plot. Okay? So that's what I'm trying to figure out. Okay? Does that make sense? Okay, so let's break out equations of equilibrium and solve. So here's my little element. Let's sum forces in the y direction. What do we have when we sum forces in the y direction? I got V going up, V plus dV going down. What else do I have going up? I don't have W going up. I have to idealize that into a point load, right? So it's W over the width, W times dx, okay? So I've got V plus this equals V plus this. Well, the V's cancel, so the change in shear equals that, okay? Now I can do the same thing with the moments, okay? Now something happens with the moments, and so I know there's a lot happened when I just sort of click the slide. Let's just sort of walk through this. So I'm summing moments. I got to pick somewhere to sum moments from. It doesn't really matter. I can sum moments from anywhere. So I just picked like the right side of the element. So what do I have? I have M going this way, M plus dm going this way. So there's that. I've got V times this distance right here. I don't have to consider this one because if I sum moments from the right side of the element, it goes right through, okay? Now, what's going on with this distributed load? Force times moment arm. Remember, I can idealize that as a single load going through the middle, W dx, and then the moment arm is half that element width. Everybody okay with that? So, do all the algebra, I get M plus this product equals that. And what is this product? W over 2 times dx squared. Now, why am I crossing this through? What is dx? It's the width of that element. And what did we say in calculus land, bless you? What did we say? Dx is very, 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 very small. Let's go back to arithmetic. What happens if you take a really, really, really small number and you square it? You get a really small number, right? So much so that that is, we call this a higher order term. It is so negligible in the behavior, it's zero. We just cancel it out. Okay? So now we have some pretty basic expressions. And this is the real relationship that we're trying to generate, the relationship between loads, shears, and moments. Okay? I propose that, and both are sort of useful, but it's the integrals that are going to be useful for the construction of shear and moment diagrams. But we can now have sort of a two-step relationship. If we look at between loads and shear, we got that dV equals W dx. Just divide both sides by dx, and boom. We get that the derivative of shear equals the load. But what's more useful is the flip side. The more useful is that if we integrate the load, we get the shear. Okay? And this is where the graphical approach is going to come into play. Essentially what we're going to do is that we take our free body diagram and we quote-unquote integrate it, we will get the shear diagram. And if we take our shear diagram and integrate it, we will get our moment diagram. And that is really the key to this graphical relationship. Now, I want to be clear, okay? For the most part, we're not actually going to be computing derivatives. We're not actually going to be computing integrals, okay? And even when we do see differentiation or integration in this class, it is going to be incredibly basic stuff. You will never see me say, solve the integral of tangent e to the x from 0 to pi over 4. Like, we're not doing that type of stuff in here. The only integrals that we will deal with are polynomials. And by the way, these are integrals that are great uses of the Casio FX115 ES Plus or similar scientific calculator because it'll just chug it out for you. Okay? Like, you don't really need to chug it out. A lot of the hard work in this class comes with setting up the integral and then let that do it for you. You've already proven that you can take integrals. You did that in Math 229. You're going to need to do anything that more complicated again. Now, that being said, while we're not going to be needing to perform the differentiation and the integration, understanding that relationship is a great spot check for deriving formulas, because when we start deriving formulas for moments and shears, you're going to be able to look at them and go, wait, that's the derivative of that. And it's a nice little check to make sure that you're doing it correctly. Okay, now, the spot check's nice. What's really, really important is graphical patterns. Okay, let's have a discussion about the graphic patterns that I'm talking about. super basic Calc 1 question. What is the derivative of x squared?
2x.
Everybody's asking me like 2x? It's 2x, right? Yes, it's 2x. What is the derivative of 3x squared?
6x.
Okay. Now let's start generalizing this. Would you agree that if I take the derivative of a polynomial and the highest term in that polynomial is an x squared term, if I take the derivative of that, the highest order term in the answer is x to the first power. Does that make sense? Like if I take the derivative of 2x squared plus 7x plus 3, the answer is going to be what I say, 4x plus 7, is that what I said? Whatever I just rattled out. I just rattled out a polynomial. But the highest order term is going to be an x. Is everybody sort of following with me on that? Okay. If I graph y equals x squared, what does it look like? What's the graph? What's the name of that curve?
Parabola.
A parabola, right? If I graph y equals 3x squared, what does it look like?
Skinnier.
But it's still a parabola, right? Would you agree that if I graph a polynomial where the highest term is x squared, it's a parabola? Okay. The derivative of x squared is 2x. What's the graph of 2x look like?
Straight line.
It's a line, right? Let me ask a more general question just to make a point. If I have a parabola and I take the derivative of that parabola, is the graph linear? With me on that? Would a fair statement then be that if I integrate a line, I get a parabola? What if I integrate a parabola? Do I get a cubic function? Make sense? That is what I think is most important, is understanding that pattern. So for example, if I have a cubic function and I differentiate that cubic function, I get a quadratic function or a parabola. If I have a quadratic function and I differentiate that, I get a line. If I take that line and I differentiate that, what is the derivative of 2x? It's 2, right? So the derivative of 2x is 2. What does the graph of y equals 2 looks like? It's constant, okay? Understanding those patterns. I'm not saying you're doing calculus, but understanding those patterns is really, really important to being able to recognize a shear and moment diagram. If my point is not clear, I'm going to go back to this slide. Do you remember how I said that with AI, I wanted you to be able to recognize whether or not a moment diagram looked correct? Let's think integrally. The load here is 0 between here and here. What is the integral of 0? It is 0 plus c, right? It is a constant. And what is the graph of a constant? A horizontal line. What is the integral of a constant? Cx plus a constant, which is y equals mx plus b. You see what I mean? Let's talk about this region right here, okay? Let's think about this. Let's talk about this region right here, okay? What does the load look like? I have a constant load right here, but I'm going to say the load is negative because the load's going down. So let's think about this. The load is -2. What is the integral of -2? I'm asking, what is the integral of -2? I mean, let's think this through. What is the integral of -2?
-2x plus c.
Oh. If I were to graph y equals minus 2x plus c, what would it look like? A line with a negative slope with some y-intercept? How about this? What about right here? What is the integral of negative 2x plus c? What is the integral? It is what? Some other constant? Is that right? What does the graph of y equals this looks like? It's a parabola. It's a parabola that opens downward because it's a negative x squared, right? See what I mean? I'm not asking you to do the integration. What I'm asking is, do you kind of see how you're going from a uniform load to a linear shear diagram to a parabolic moment diagram? That's what I'm asking, okay? If you understand those patterns, the graphical approach, you're already halfway there. That's what's important, okay? And we're going to break those down step by step over the next couple weeks. Sound good? That's all I've got, everybody. I will see you all on Friday. No, I'll see you tomorrow.
How long did it take you to get?